Welcome to one more video on radio frequency integrated circuits. So in this video we shall see the applications of splitters and combiners which are operating at RF frequencies. We know that usually the RF lines will be of 75 ohm impedance. Assume that we want to amplify a signal which is on this RF line which is of 75 ohm. So assume that this is the amplitude of the signal on this 75 ohm RF line. So if you want to amplify this signal, one of the possible architecture is the possible circuit is you pass this signal available on the RF line which is of 75 ohm through a splitter circuit. So this splitter circuit is one, so where it is perfectly matched to the impedance of RF line which is a 75 ohm, and since we have to amplify the signal, we need to have amplifiers. Usually amplifiers are will have a impedance of 50 ohms. You can see this is an amplifier of 50 ohm. Now we have amplifiers whose input impedance is 50 ohm over here. Now since we want to amplify the signal which is there on a RF line of 75 ohm, so first and foremost thing is that this 75 ohm cannot be directly connected to this 50 ohm amplifier. So we need to pass it through a splitting circuit, so whose output impedance is 50 ohm and 50 ohm. Now since this is the output of the splitter circuit whose output impedance is 50 ohm, can be perfectly matched with this amplifier of 50 ohm here. Now we can say this is 50 ohm, this is also 50 ohm, whereas the RF line is 75 ohm. Now this is a 75 ohm input splitter line. So the output has been split into, okay, the input which has been fed at the input of the splitter which is 75 ohm has been split into 50 ohm output lines here. So these are the 50 ohm lines. Now you can see, now since it is an amplitude, assume that okay, this is amplitude, since it's a splitter, you can see here the amplitude has reduced. So certainly the amplitude of both the splitter outputs are reduced here. Now you can see it is a reduced amplitude. Now since it's an amplifier of 50 ohm, so there's a perfect match between the splitter output and the amplifier input. Now you can see this is amplified to an required extent. Now here also you can see this is amplified to an required extent. So this split output has been amplified by these two amplifiers which are connected to the output of the splitter circuit, and since the output impedance of the amplifier is also 50 ohm, it is now in turn connected to a combiner circuit whose input impedance at this point is 50 ohm. Now there's a perfect match between this 50 ohm and this 50 ohm, and this 50 ohm and this 50 ohm are matched. Now we know that whatever amplification we have done it for that 75 ohm RF line has to be given back to that 75 ohm RF line. You can see here, now this is again a 75 ohm, so this 50 ohm which has been used to take the signal from the output of the amplifier, so there's a perfect match here. Now this should be again 75 ohm, so that this can be connected to the RF line of 75. Now we can see the amplitude of this much magnitude has been increased to a large extent of the output amplitude has been increased here. So it's a application of a splitter cum combiner. You can see the first part is a splitter one, so it is now amplified with amplifiers. Most important thing is that the matching of the impedance of the amplifier and the splitter output, and again amplifier output and the combiner input, and finally the combiner output impedance should perfectly match with the RF line impedance which is again 75 ohm. So this is a combination of splitter as well as a combiner in amplifying a signal on RF line. Let us take up another example where assume that I have two RF signals, RF1 and RF2, which are on a 75 ohm RF line. You can see now I want to have only RF1 at the output, or only RF2 at the output, or I can make a combination of RF1 and RF2 at the desired timing. So what we are doing here is that, so we are taking two RF signal inputs which are connected to 75 ohm combiner here. Now the both the signals are combined. Now it is passed through a gallium arsenide switch. So gallium arsenide is a 3-phi semiconductor which will operate at very high frequency. Its switching time is very low. Since it is RF frequencies, we are not using a silicon switch. So this is a gallium arsenide switch whose mobility of the electrons in these components in these devices are very high. Now you can see, depending on the control 1 and control 2, a particular switch will be operated, and this combined output will be passed through a band pass filter to select RF1 output. Now we can see this is again 50 ohm is a band pass filter output impedance is perfectly matched this in this combiner here, and this is the output of the gallium arsenide switch, which is taking the input as the combination of two RF inputs, and we have this output is being passed through the second band pass filter to select only RF2. These two are combined here, and of course we can have varieties of possible output over here. Either you can have only RF1, or you can have only RF2, or you can have the combination as we see in the next slide. Now assume that this is RF1 at a particular frequency which is bit high frequency comparatively. RF2 is a bit low frequency signal. So since it is passed through a combiner, so assume that this is an overlapped signal like this. So it's a combined output at the combiner, and assume that if the control input is like this type of square wave for an input 1, for input 2 if it is like this, whenever input 1 is high, so let us assume that at the output of the final combiner, so we have the output corresponding to RF1, and whenever the control input 1 is high, so we'll get the output from we'll get at the output the signal from RF2. Likewise, using this combination of combiner and one more combiner, it is possible to get the desired type of signal at a particular line. So from two RF lines, so from two RF inputs I can get a desired one. It is also possible that, assume that I'm making only the control input 1 as high, and if this is low, I'll be keep getting only this signal. Whenever if I want to get RF2 signal at the output of the last combiner, what I can do is I can make only the control input 2 as high and make 1 as 0. So I'll be keep getting only the RF2 input at the output of this combiner. Meaning, if I make this always 0, and if I make control input 2 as high, so I'll be getting only this signal. Suppose if I make it like, okay, 1010, so I can get whichever bit is 1, I'll be getting that corresponding RF input, because we have a band pass filter which will select a particular frequency out of these two signals. Now in this way we can use a combination of splitters and combiners for various applications. We have seen two applications, of course, in the previous slide, previous video. We have seen how does the same signal can be passed on for different analysis in case of a satellite received signal. So most importantly, other than combining and dividing, the impedances of the input and output ports of the adjacent devices have to be perfectly matched. Now this is a gallium arsenide switch of 50 ohm, so this should be perfectly matched with this one, and this is again a 50 ohm band pass filter should match with the 50 ohm combiner here. So of course we are using this as a combiner in both these cases, but in the previous example we use this as a splitter, and the same can be used as a combiner here. This way we can able to use the splitters and combiner in RF circuit applications.